Okay, so Bessie is running a race of length k meters. That's 10 to the ninth is a very would make it a very long race. But she starts running at a speed of 0 meters per second. In other words, she's stationary. In each second, she can either increase her speed by 1 meter per second, keep it unchanged, so she keeps going at the same rate, or she decreases it by 1 meter per second. So basically, she's either accelerating, not accelerating, or decelerating. For I remember in physics, they would tell me that like deceleration is a lie, and that there's only positive acceleration or a negative acceleration. But anyway, a weird random fact. I'm not sure if that's true, actually. I might be remembering wrong. But anyway, for example, in the first second, she can increase her speed to 1 meter per second and run 1 meter. So now she's moving at 1 meter per second, or she could keep it at 0 meters per second and not move anywhere. So that makes sense. Like she has those options. Obviously, you can't go negative. Otherwise, the problem will become way too complicated because then you could just, you could get stuck in a loop. You could go positive 1 meter and then you could go negative 1 meter and you never end up going anywhere. So Bessie will always run towards the finish line and she wants to finish after an integer amount of seconds, so ending either at or past the goal at this integer point in time. What that means is that it's kind of like the opposite of a race, like a race in real life, because when you race people, you're like, you know what, they give you a time limit and you're like, I want to finish this before the time limit's up. But here it's after, so I guess that's a weird race. But anyway, furthermore, she doesn't want to be running too quickly at the finish line. At the instant in time when Bessie finishes running k meters, she wants the speed she's been running. She wants the speed that she's been traveling to be no more than x meters per second. So Bessie wants to know how quickly she could finish the race for n different values of x. All right. So basically, you want to find out how many. Yeah, basically what this says. So the variables you have to keep in mind, because they're just letters, so it might be hard for you to like wrap your mind around them initially. I know it was hard for me. Is that the speed is the length is k, so that's how much she has to run. Her speed doesn't actually have a variable, but it's not necessarily the maximum speed, but the she wants the race to end at x meters per second. So just remember k is how long the race is and x is what the finishing rate is. And she wants to know how quickly she could finish the race for up to 1,000 values of x. So you could see that there's a lot of possible values of x, but you can know it only goes up to 1,000. So you have that on your side. So be very good. Do pay attention to what this section says, the scoring section. I know some people have the tendency to just be like, you know what, like blah blah blah. I don't care about scoring. Let's go to input format. But if you are on a time crunch, you could see that test cases 2 to 4 satisfy blah blah blah. So that must mean that, if you can't come up with any solution, so you're just staring at this and you're like, what's going on? Then just write a program that could solve this for sure. And then it will work for sure test case 2 to 4. Maybe it'll work a couple, 5 or 6. But I think, as I showed you in the last time I was here, you don't have to get 100% on every single one to move on to the next level. So just pay attention to this. This might make you feel a little bit better. You're like, oh wait, so I got 100 on the other ones. Maybe I don't need to get all 10 on this one. So I could just focus on this. And if getting 4 out of 10 right and moving on to silver is much better than trying to write a program not writing a program at all and not being able to move on to silver. So anyway, we have input format race.in. We have k and n. So the next n lines contain a single integer x. So basically what they're asking, this is really weirdly written because, every time I hear this kind of wording, I'm like, you know what, I have to find all possibilities of n, but apparently what they're just telling you here is that they'll list the values of x for you, which is a little bit nice. But it's nice of them to do it. All right. So it says, remember, k is the distance and x is the maximum speed you need her to be running at any given moment in time. And then so yeah. And so basically you're trying to find an optimal solution. So how quickly she could finish the race. Again, it's not very clear. So it's very important that if you don't understand what the question is asking, like this is really vague, in my opinion, you have to read the input and output to make sure you get it 100%. Like I know it seems obvious and you might have known this already, but not all people do. So I just wanted to let you know, just in case. We have output n lines, each containing a single integer for the minimum time Bessie needs to run. K meters of blah, blah, blah is less than or equal to x. Okay, so it looks like here, the minimum time Bessie needs to run k meters. It looks like here, right? If she finishes with a speed less than or equal to x, it seems most rational to, in the first second, right? We start at second 0 and then we increase our speed to 1 meter, which is, we increase our speed by 1 meter per second. So she's actually moving 1 meter per second. Actually, I think it would be better if I did with slanted lines. So I do that. So she's moving 1 meter per second. Hopefully you guys can see my illustration. If you can't, just please let me know. So 1 second, so she can only increase her speed by 1 meter per second. So at 1 second, she's like up here. And so she's traveled 1 second. So now she's traveling twice as fast because she's now traveling 2 meters per second. So she's now at 3. She kind of stays there, right? Don't think of it as a flat line because then you'll think, wait, she stopped. No, that she hasn't stopped. She's still moving. She just hasn't accelerated. So we go to 5. And then so we go up here. But at 7, we can't keep accelerating to 9 because then we have to slow down. What we want to do is, actually, we can't keep accelerating to 9. My bad. So we keep accelerating to 9 and then we slow down. So basically if you've ever learned integrals and derivatives in calculus, it might help you a little bit to think of the speed as you basically plot out the derivative, which is her speed on there, and then you calculate the area under the curve. So you're trying to maximize the area under the curve. You're trying to make it go up and down and up and down and up and down, like that. So obviously, so that's how the problem set up. And now all you have to do, and they give you examples here. And then, they give you examples here. All right. So you're like, okay, well, I don't really know what's going on. I don't know how to do this problem. So one thing you might notice about this problem is that you just have to think about it rationally, because theoretically there's an infinite number of things you could do, right? Like, remember how I was illustrating, you could go up and down, like you make it look like a mountain range. You could do that, but that's not the most optimal method. Because we are assuming she can't get tired, so there's no reason for her to slow down. So the optimal curve, it would seem like, is that we go as fast as possible here. And then whenever I close to the end, we drop off. That would seem to be the most rational method of doing it, because you want to, again, maximize the area under the curve as much as you can without having it exceed the point X, which is right here. We want to have our curve return here at the very end. So obviously that doesn't mean that we could go as high as possible. Like, we could just keep going faster and faster, faster and faster and faster. So basically what we would want to do is we would want to speed up, right? Well, let's see why. Okay, so you're like, well, why can't we go to 3 meters per second? It's because another thing you have to consider is that Well, okay, were we to go up without bound, we would also have to consider the fact that we might not be able to come down in time. And what I mean by that is, let's say that we on step one we decided to move up one, so when we moved 1 meter, we decided to go up again. There we go, 1, 2. So now we're moving at 2 meters per second. So our running sum is 1, 3, and we decided to go up to 3 because faster the better, just like I told you earlier. Then we go up to 6. The problem is, I mean, if you stay at 3, you're going to go up to 9, right? Moving another 3 meters per second. So obviously, you're not going to be able to come down in time. If you do try to come down to 2, right? You come down to 2, you would have moved up to 8. And let's see, you could, and then you would have moved to 10, and then it would have been a little bit, and then you would have exceeded the limit because you're going down, and then yeah, you're going down, and then while you're going down, you're still moving, and then so you kind of exceed 10 by a little bit. So we won't do it like that. So there is a little bit of a trade-off because of this requirement at the end. Because in theory, the fastest way just to get anywhere is just to speed up as much as possible and not to slow down. It's kind of like if you're not in like it's like the fastest way for you to go somewhere is to like take a train that doesn't have brakes. Like yeah, that's basically the fastest way to go anywhere. Unfortunately, though, you want the train to slow down so that you don't like that. Yeah, because if you reach the station, you want to make it nice and slow rather than crashing into a wall or something. All right. So that is yeah. So when you're doing this, I think the main takeaway from this is that you just have to think about the shape of the question, basically, or like the most reasonable shape that the answer is going to take. Like, if they ask you, find the best solution to this, obviously, like there's a lot, like don't get overwhelmed by, I don't even know where to start. Like, think about how you would do it if you were Bessie. Like, how would you like how would I try to optimize my output? And you'd be like, well, I tried to go as fast as possible as soon as possible. So that means no dilly dallying at like 0 meters per second, no wasting time. Just go, I ramp up my speed, and then at once I'm at the peak, I kind of stay there, and then I ramp down my speed. That's basically the idea behind it. All right. So, and then once you figure that out, you're like, oh wait, maybe. And then if the answer becomes a lot clearer, at least now you have a potential way uh, to solve the problem rather than just being lost. Okay, so let's go ahead and write this. All right. I'd also like to mention that 2020 is the last year that they make you use the file input. So we're going to use different kinds of input for the two problems that we're going to do today. And it's not because the problems are different, it's just because the way the contest was set up in those years. All right. Oh, and I realized I just pulled up my old program from I think Tuesday, and I forgot to post the programs from Tuesday, so I'll do that right after class is over. Yes, apologies for that. I did post a video so you can watch it to your heart's content whenever you feel like. All right, so let us begin the problem. My screen share does not want to cooperate with me today. Anyway, so we will start off with our Java code. I'm going to write it in Java anyway. So java.io, and then import java.util. When you write as you'll see today, you don't need to import java.io anymore, especially in the more recent contest, excuse me. But you do need to keep importing java.util because that's where stuff like hash map, array list live. So you do need to keep importing this, but you could kind of drop this when you actually take the contest because we won't have to do the file reading anymore. All right, so public static void main string args. We'll set up our scanner. If you don't remember the pattern, just pull up your old problems. All right, and now I'm going to read all of the questions. Sorry, all of the variables. So I'm going to do int k equals s dot next int n equals s dot next int. And then from obviously out of that we have obviously out of that we're going to have to read the next. You're going to have to read the x values. So for int I equals 0. We'll change the I variable. I don't like using I variables in the outer loops because I think I might have told you last time. But if you use up the I variable, you can't use it in any inner loops. And it's like I don't know about you, but I have like muscle memory to use I in all of my like indexes and stuff. So I do end up using this I when I should be using an inner for loops variable. So it's just really irritating for me. So I tend to use a different variable, but yeah, I'm, I'm probably spending more time thinking about the name of the variables than actually writing the code. All right, so I'll change the value of this. I'll change the name of this variable if I keep making mistakes. So, oops, int x equals s dot next int. So basically, we do want yeah, so we'll make a couple variables as we go on. So let's see. Excuse me. So the very first thing we have to do is we have to start moving. Because if you think about it, right, it doesn't like, our time base, if you think about it, our time basically starts the moment that we start moving. And technically the problem doesn't tell it to you that way. But I mean, Bessie could spend 10 seconds waiting, 50 seconds waiting, and it doesn't change the answer because remember, we're looking for the optimal time. But basically, Bessie might as well not have stopped in the first place. So whatever time we spend not moving, we can just discard. So that's why. So you're like, okay, well, what does this have to do with the problem? That means that we don't have to care about any time we spend flat at 0. We basically start counting at 1. So that's why my speed is going to be equal to 1. And then I'm going to do int distance is equal to 0. So I'm going to make an infinite loop. It doesn't matter. This is a funny looking for loop, but you could also use a while true. It's just a funny looking for loop it's the same thing as this for loop. I just don't have anything inside of it. You know what? Let me just turn it in less confusion. Let me just turn it while true. But you could use a weird for loop if you want to write less characters. So you could do distance plus equals speed. So obviously we want to, so obviously we want to be able to do, obviously if distance is greater than or equal to k, we will do print ln. Oops. So print ln. I don't know. We'll do. We do have to keep track of how far we are in the. So we have to keep track of the time. So we'll do time equals 0, and we'll do time plus plus here. So basically, this is how basically we keep accelerating, right? This is basically the setup of the problem. We're just doing what the problem is asking us to do. You can see that we state the speed. After this if statement, we have to play around with the speed variable. But for now, this is just what I spelled distance wrong. This is basically what the problem is asking us to do. Bessie moves, this amount of distance with this kind of speed and then time, and then we make the time go forward by 1. So we will do time, and then we will break out of the loop. All right. So basically, if our basically we always want to go up to num. We always want to go at least up to our target speed. So if we're less than that, if we're less than our target speed, we want to go, we want to keep increasing our speed. Yeah, so if speed is less than x, we do speed plus plus. So now, okay, so you're like, well, okay, well, uh how should I speed up the cows in the future? Well, basically, if you think about it, right? If I go up, so I'm going to introduce a very interesting way of thinking about it. If you think about it, right? A Let's say that I start at speed 1 and I go up to speed 2 for a couple seconds and I come down to speed 1. So let's say I spend 5 seconds here, 10 seconds here, and 5 seconds here. If you think about it, right? Okay, I stopped at speed 1. You know that because I drew it back. But as far as like the average speed is concerned, we're going at 1.5 meters per second, as you can see. And that's very interesting because you're like, well, okay, we're going an average speed of 1.5 meters per second, but we do it by going up from 1 and then to 2 and then back to 1. It's like, it's like basically this is slow and steady wins the race. And in this case, this is like the tortoise and the hare, except it's not really like the tortoise and the hare because end up both like they're technically going at the same average speed, so they end up in the same location at the very end. Basically, so you could do all sorts of crazy maneuvering in the middle, but you could see that and no matter what you do, if you go up and if you go down, you're going to have some kind of average value, right? So you spend some time ramping up your speed, and then you want to end somewhere here at this rate, and then you go up as high as possible, and then you go down as fast as possible. But you can see past that, we have an average speed, and it's going to be a little tricky. Basically, we kind of do want to discover the average speed, kind of like that. So it's not exactly we go here and go jump up directly. Basically, we're going to kind of ramp up and find the average speed, and we're just going to pretend we're at the average speed, because built into our assumption about the average speed is that we're going to exceed it for a little bit, and then we're going to go less below it for a little bit. I want to make sure you just make sure that you get the concept, because it's not something that's 100% intuitive to everyone all the time, but it is a useful trick, especially if you're like, okay, especially if your brain is all like fried and thinking about, okay, when does my, okay, when should I ramp up the speed and when should I ramp down the speed? Yeah. So changing gears for a little bit, I'm sure at some point your teachers have dragged you through practice it. I know I've dragged some of my students to practice it. And there is this weird section in the book, or I guess it's based on a textbook, so that's why I call it the book. But there's this weird problem where they start asking you about doubles, and then they're like, oh, and the whole moral of the story is that doubles are imprecise. It's like, there's a famous example going around. If you add a 0.1 and 0.2 using doubles, you're not going to end up with exactly 0.3. You're going to end up with like 0.3000001. It's because floating point numbers can only hold so many digits. So at some point you start running out of digits. They don't hold digits the same way that our numbers do. So they're kind of imprecise in that way. But anyway, so I would like to stay away from floating point numbers if at all possible, because there's weird things with the rounding. Like, because you're imprecise, what if my solution, what if I use math.floor? What if my solution, what if I intended to be 2.0, but because of imprecision, it goes down to 1.99999? And I don't really want that. And if I do math.floor, it's going to round it down to 1, which would cause really mystifying errors. So what I want to do is I want to keep it to ints. And basically we could I want to divide these into thirds because if you think about it for long enough, I have spent 34 minutes on this, so I want to move on to the next one. But I want you to spend some time thinking about this and prove to yourself why it works um why it works in halves, basically. So not thirds, sorry, halves. So basically, because it works because hint, you spend half the time, you think about it, you basically there's like a you could see the gap between here is equidistant. And then you could imagine that we might spend half the time at this one speed and half the time at this other speed. So just try to prove to yourself why this is the case. So basically, we're going to do int fraction. So we'll do otherwise. We'll make the fraction go up by, basically, we'll make it go up by half. And if we have two halves, right? 2 over 2, we will do speed plus plus, and we'll do fraction equal 0. And then we're going to go, yeah. And then we're going to go back to what we were doing before. So we're going to do out.close at the very bottom because I forget this a lot. So you can see this is another way of doing fractions and floating point without actually using a double. And it works because like fractions, if you think about it, are just whole numbers on top of each other. Like the numerator is a whole number, denominator is a whole number. Everybody's nice and happy. So yeah, this is actually fairly common in high performance programming. I use this strategy a lot. Yeah, when I program, especially when I need to make things run very fast, not related to sometimes not related to USACO, but other things as well. But anyway, so this is our solution. So you can see it's a lot simpler than you imagine. Like it's not like, wow, it's like the longest program that not the I will tell you that the longest USACO problem that I've written so far was the December 2022 one, the one that just happened last time. And I don't think that one was over 500. Sorry, I don't think, let me check how long that was. Okay. Let's see. Yeah, it wasn't much longer than, it was shorter than 150 lines. And there you can see there's a lot of debugging comments. This is not the best way to remove things from an array list, but you could see most of the problems are not that long. So don't short circuit your mind thinking that this is going to be this insanely difficult question that like nobody is supposed to understand. If I had a chance to rewrite this because I was writing this in a hurry because like I was doing this with the class and they're like, I want the answer. And I was like, oh my God, I have to write fast. So if I had less of a time crunch, I could probably write this a little bit neater, but you could see these are not that long this is not that long of a question or long of an answer. This is not that long of an answer. This is like 40 lines long. And I have a bunch of empty lines here. Yeah, so don't get intimidated by how difficult the problems are. You will not be writing an enormous amount of code. Yeah. All right. Anybody have any questions? Okay, so in that case, I'm going to save this and I'm going to upload it to make sure it works. And in the meantime, do get started and look at the next one ahead of me because it takes time for me to go and submit it. And I have to log back into USACO again, so which would take me even more time. Okay, let's log in. Okay, so while it's grading, I'm gonna move on to the next one because I mean, like, I'm just looking at a spinning wheel right now. Oh, and I forgot to, if you haven't done it already, put throws IO exception on main, just like you've done for the last couple of problems. I forgot to do that because I don't have those squiggles under my code. I write this all by, yeah, I write this all through, I just write this all myself. But anyway, the next contest is, let me see, we're on December 2021, so there's luckily no more of the IO exception stuff going on. We're back to just using scanner system.in and then scanner system and then system.out.println, which is very nice of them. Let me preload it into the window first. Let's see, I think it's this one. Okay, so I've confirmed that this solution, the solution that we just worked on, does indeed work. All right. So 2021, uh, we're in 2021, so we're now within recent memory. So anyway, it says blah blah blah. They have their alphabet, blah A through Z. She lists these and specific ordering that might be different from the A B C D blah blah blah. A word of advice for people that are taking ACSL. It doesn't really have anything to do with USACO, but this just reminds me, if you when you are doing contest 3 and you're doing data structures, I'd highly recommend writing out all of the letters. So people always tell me that they know the letters of the alphabet and they know the orders, but they always keep forgetting things. Like they keep putting K after N, or they put R before O, and then that's why people that's the reason most people make mistakes on those problems. So always write out your alphabet if you're doing ACSL contest 3 data structures. You will it seems like a wasted time, but it only takes 5 seconds and you will be surprised how much it helps. But anyway, so to pass the time, Bessie the cow has been humming the blah blah blah, and he's curious how many times she's hummed it. So given a lowercase string of letters that Farmer John has heard Bessie say, compute the minimum number of times Bessie must have hummed the entire alphabet in order to have heard the given string. The Farmer John isn't always paying attention to what Bessie hummed, so he might have missed some of the letters that Bessie has hummed. So the string you are told just consists of the letters that he remembers hearing. Okay, well, this makes it kind of difficult for us to do, but yeah, we could do it. It's not that difficult, or it's not 100% extremely difficult. This is the first line of input contains the 26 letters A through Z in the order that they appear in the alphabet. The next line contains a string of lowercase in the order that they appear in the alphabet. So this is very important if you're reading through it. It tells you that you know the order of it already. So it's not one of those problems where they're like, find all of the possible orderings of the alphabet or figure out one of the n to 50 gazillion billion orders of one, on the possible orderings or like most optimal ordering, blah, blah, blah. So you could see that you could kind of breathe a sigh of relief when you see that. I mean, I did. So the next lines contains a string of lowercase letters that Farmer John has heard Bessie say. So the string has length at least 1 and at most 1,000. All right. So if you take a look at this for a little bit, you could see that you might be able to see a pattern form. Okay, so just keep in mind this is the alphabet and this is this is the string that we hear. Yeah, we hear Bessie say. It luckily says minimum number of times so that we don't have, like, technically, Farmer John could have heard the M and gone on a sabbatical and come back after 2 years and heard the O. So we're not interested in the maximum number of times, we're interested in the minimum number of times. What that means is that you can not have, let's say, another, because basically we hear Bessie repeating the alphabet in a row. So basically you can't have you have to find the closest letter to the O. to M closest letter in this direction. So what you can do is actually you could turn it into a little bit of a belt. And what I mean by that is imagine you have a conveyor belt. So basically we're always feeding characters in this direction. And then after we reach the end, we start again at the very beginning. That's one way we could, that's how you have to imagine it. It's too difficult to imagine an infinite string. And honestly, imagine if you're, yeah, it's too difficult to imagine a infinite length string. So just imagine you're just going in a circle, you go M to O, and then and then you start again in this direction. So you kind of run in a, yeah, kind of like those levels in Doodle Jump if you've ever played the game. Like you go off the side and you just end up on the other side. Kind of like this. You go off the side of the screen and come in on the other side. So yeah, that's pretty much how you do it. And then basically you just count so basically you count how many times you go off the side of the alphabet. So it looks like, let's see. In our case, we have the word mood. So we start M, we go to O, and then we hit the side, we hit this N, then we go back again. We hit this O again. So that's we hit the M, O, O, and then we keep going here, and then we hit it up. So we go through it 2 times, and we end up here at D. You have MOOD. So you could see that even though we go off the end of the array twice, we actually do end up going. Sorry, we do end up we do end up reciting the algorithm. Sorry, the alphabet, not the algorithm, the alphabet 3 times because technically the first time she recites it counts as a time. Yeah, so that's basically the idea. So you're like, okay, well, this is way too easy, right? It can't be that easy. Surely there has to be something that would screw us up, like maybe time limit exceeded, not memory usage, because like you could see, if we just stick to this one array, we just go off the end of the array basically, and then we come back to the beginning. So let's see, it has a string length of at least 1 to 1,000. So think about it. What is our worst case scenario here? Our worst case scenario is that if we have like a string just full of A's, that means that we have to run through all 26 letters of the alphabet and start again. So there's no case where we could start at M and just hop over to O and it's like, oh, hey, happy coincidence. Like the string has, so you could see that there are 26 letters. There are up to 1,000 letters in this string. So you could see that the maximum number of times, like think about the worst case scenario when you're doing this. Like don't think about, what's my usual scenario because, they'll show you usual scenarios for most of them. But in this case, yeah, they'll basically, they'll throw a worst case scenario at you at some point. So you just be mindful of that. So you could see 26,000 iterations of a for loop is not that much in terms of computing power. If you're concerned about if that seems like a number that's too large for you, write an empty for loop that runs 26,000 times and see how long it takes. It shouldn't take more than a blink of an eye. You could see the alphabet is the same as a normal alphabet, no additional constraints. So I don't know why you wouldn't want to try to aim for that 10 because if the algorithm presented here works for any ordering. Yeah. Okay. So let's go and write the program. All right. So I'm sure there is a better way to do this. There is a way, I'm sure you could use you could probably leverage arrays and then you could you could actually write an inverse lookup table where where you're not looking particularly at you're just looking, you're not looping through the array, you're just looking up the indexes and comparing them. But I'm just going to show you this method because it's the simplest one basically. It might be something that you might come up with too. Like you don't have time to think about inverse lookup tables. You want to do this problem as fast as possible. So let's go ahead and do it. Let's go. Public class uttered. I don't know why they call it uttered when it's that. I would have called this a alphabet question, but that's random naming schemes. You know what? Let me call this uttered calphabet. Calphabet. Oh, it's not calphabet. It's calphabet. My bad. So java.util public static void main string args a scanner s equals new scanner system.in. Our very first order of business will be to look inside of our string. So we make string s equal string alphabet. I'm not going to call it alphabet. I'm just going to call it alphabet. You go s dot next and string stir equals s dot next. So we have that. So basically, we're going to have it's a two pointers question. Basically, we're going to have one pointer that's running through this string. Pointer is just, you could think of it as an index as far as Java is concerned. Just think of, yeah, it's as far as you're concerned. If your teachers have ever gone over two pointers in Silver, it's just you have nested for loops and the pointers are a little bit more complicated than like just a regular two-dimensional array. So in this case, we'll have, I guess, two for loops actually. But we'll play around with it a little bit. Yeah, we'll play around with it for we'll play around with the pointers for a little bit. So we'll put int index equals, you know what, actually, I'm going to give them something. The outer loop, I'm going to call it int I equals 0, I equals length, I plus plus. And then I will have another index here outside. I don't want to keep it inside because if we keep it inside, it'll keep resetting to 0 whenever we strike the letter. Whenever we move to the next letter, I meant, not when we strike the letter. So int outer equals, we'll start it at 0. And of course, we need a count for how many times she said the alphabet. So we'll count equals, you know what, she starts with 1. So, I mean, she has to say it a first time, so we'll just stick with 1. So we will loop through the array. Actually, you know what? Let me rethink my loop structure. Actually, let me rename this. Actually, I just realized this is not the best way to rename it. I will call this the alphabet index, and then we'll call this the stir index, both corresponding to each of these two string variables. We will do while string, stir index is less than stir dot length. And then we'll check if this is, we'll basically keep running until we run out of strings to letters to compare. So we'll do if stir dot char at stirring index is equal to, yeah, alphabet char at alphabet index. That means that we have hit a match. So that means that we can make our string index go up by what? Like that, just like that. So that means that we have hit the appropriate letter in our, you know what, I could draw it out using this diagram. I'm gonna copy and paste this. So if this is alphabet, this is our mood, or this is our string. So you could see that we would have kept going this way until we discovered our M. So this would be our alphabet index, and then this would be our string index right there. Let me put it on a different line. But we do want to increment our alphabet index, oops, index by 1. And if it's equal to is equal to 26, we will indicate that, okay, Bessie finished reading her alphabet. So alphabet index equals 0. So that means that she's going to start again at the very beginning, but we're going to make our count go up by 1. And then at the very end, we're going to do system.out println count. And I will save this, and I will test if I will make sure it works first before I try submitting it. Because yeah, this one, I will be honest with you, I have not tested yet. I am fairly certain that it works though. I haven't tested this version of it yet, or is how I should put it. Let me. Okay, there we go. Okay, so it looks like it produces a right sample input. So I'm going to now test it on the real input. Let's see. And let's see how it works. All right. So you could see that this is not that difficult of a question. It's just a little bit, you could see that the question is like, it's 33 lines long. So it's not actually that difficult of a question. And you could see while it's not the most efficient method, it's the one that it's still everything fits within the time limit. So I think one thing that you should walk away with today is that first, these problems are not very long. This one is 40, this one is 30, 33, and I have this whole big comment over here taking up room. So these are not extremely long questions. These are these are pretty simple questions. Like we were not like the setup might be difficult, but when you read it, you're like, when you read through when you actually do it, you're like, oh, wait a second, it's not that hard. So I don't want you to overthink any of the questions, but don't try to dumb it down and like try to make it too like this. Our race question took a little bit of thinking, right? Because you had to come up with the average idea. But once you did come up with the average idea, you're like, wait a second, this is like ridiculously easy. Here you're like, wait a second, we didn't like this was just extremely straightforward. We just literally did what the problem was asking us to do. We just kind of looped over the alphabet over and over and over and over again until we found all of the characters. So yeah, so what I just want you to come up with today's first, they're not that difficult. Second, you don't overthink it, and these are not. And third, don't walk into these thinking that these are unsurmountable. There is a solution to this. People have found the solutions. You're going to be one of them. So don't panic when you see it. You could see that even if you're intimidated by, even if you consider yourself a slow coder, this is 33 lines of code. And then we basically came up with the idea in like 5 minutes. So basically, if you can't come up with anything, just go for the most obvious answer. And you don't have to do the calculations that I did, because if you just try writing it and you submit it, you will see, you might fail the last 3 test cases. That itself will be evidence. This is the best evidence for it exceeding the time limit. You'd be surprised how fast your code runs. As long as there are some hidden pitfalls I get. You're like, well, okay, well, these 5 nested for loops are like they only occupy like 5 lines of code, so they don't look slow, but they could be slow. Yeah, array lists are always slower than regular arrays. So that's why people are, so that's why arrays exist, even though array lists seem to do everything better than regular arrays. So yeah, so just if yeah, so you don't always have to come up with the most genius idea possible. You don't have to like get a patent for what you've just wrote. All you have to do is just, you know, think rationally, think, don't overthink the problem, and then just go for it whenever you're ready. All right, so that is it for today. I don't have anything else for you today, but on Monday I'm checking the schedule. Oops, oops, wrong button. Oops. On Monday, you will be seeing me again for the rest of 2021 and the beginning of 2022. And then on Wednesday and Thursday, it'll be the excellent Sean teacher picking up the rest of the problems. All right. So everyone, hopefully you have a good weekend. uh, you know, enjoy it. It's the weekend before USACO, so don't panic or anything. Just enjoy your weekend, relax, and yeah. So yeah, everyone, have a nice weekend. Stick around if you have questions.
I have a question about the race problem.
Yes. What is
So,
the question?
um, for the example, case, is 1, 2, 2, 2, 1 the only solution?
It's actually, it might not be. It is an optimal solution, so it's not necessarily. So I guess you could go up to 3 meters per second and go
Uh,
spend more time ramping down. I think I showed that earlier. I thought I made a mistake, but I don't think I have. So there are other solutions. Definitely.
okay. Also, can you explain the fraction part of the code again?
Okay, yes, of course. Let's go back here. So okay, so the first thing you have to realize about fractions is that they have a numerator and a denominator. If the numerator is zero, obviously the fraction is zero, so the fraction might as well not exist. If it's equal to the denominator, like uh, let's say 2/2 in our case, you could see it's equal to 1, right? So like you could see that if you have a 3 and a 2/2, it's the same thing as having a 4, right? So
Yeah,
basically, you could imagine oops, wrong one. You could imagine our fraction as being this variable being the numerator. Our denominator is hard coded into here. We start with the numerator of 0. So let's say we start at 3 of 0/0. Oops, 0/2. My bad. Right? If so, when we start this loop, fraction equals 0, and let's say this has already been met, so we ignore that. Fraction plus plus would send us into 3 and 1/2/2. But you could see we don't actually modify the big number over here, right? Yeah.
yeah,
Okay. So you could, and after we increment it one more time, we go to 3 and 2/2. So that's when this fraction equals 2 comes into play. Remember, if it's 2/2, we convert it into +1. That's why we do speed plus plus. And we turn it into 4, but at the same time, we convert it back into 0/2, like that. Does that make sense?
yeah, but why is it if fraction is 2?
2/2
Yeah, why 2
isn't
specifically?
Oh, two, it's because if you think about it, are you talking about why it's over two or why it's two over two is special?
Why it's two? Like, why is the denominator two?
If you think about it, right? You spend half of your, so it's like think about evenness. We spend half of our time ramping up our speed, and we would spend, basically, we would want to make it look like a pyramid, right? We go as high as we can. Like we wouldn't want to make it like a plateau because it would be more complicated. But if you think about a pyramid, the average height of a pyramid you would imagine, or like would kind of look like this, right? It's like around halfway to the top, halfway to the bottom. It's a little bit fuzzy here because we actually kind of go like this. We kind of ramp up the speed, kind of like this, but it usually we spend half of our time speeding up, half of our time speeding down. So that's why we could make a reasonable guess and say our average speed is kind of half. It's kind of sort of half. We kind of spend our time kind of edging up to it. So it's a little bit less than half. It's like there's a little bit less stuff on the top than there is on the bottom. Does that make sense?
Yeah.
Okay. So yeah, this fraction method is fairly common in other kinds of programming. I have written a fraction thing before. Let's see if I have it. I don't think I have it open. I'm not gonna bother. Oops. I'm not gonna bother opening it. So, but it is fairly common in some kinds of programming. So it's just a way to keep our a whole number separate from our like the fraction in the numerator and the denominator, so that floats and doubles don't have to get involved. All right. Do you have any other questions?
No, not right now.
Oh, all right. Then have a wonderful weekend then.
Thank you. You
All right.
too.
All right, Sean, if you have any questions, just let me know. I would, oh, 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 sorry. Oh, okay. I saw your, Marcus, I just saw your chat right now. Oops. Okay, my bad. I did not see the emoji. Okay, so Sean, if you have a question, just let me know. But it says, I've received a new emoji. I don't, that's very interesting. So yeah, Sean, just let me know if you have a question. Or maybe you got stuck trying to leave the meeting.